Let me chat with them.
Because if it doesn't come up on my screen, I can't put them in. The only way I know for it to come up on my screen, there's Shelton. So he finally popped up on my screen. So he should be in.
Okay, perfect.
Yeah, the best I can tell is I'm looking at this thing. It says 5:30 to 7, so everybody should be able to get in. I think with the time change, somehow whatever's keeping track of this messed up when the time switched, and so all their 6:30s got moved to 5:30 somehow. Yeah, that's what happened, because my other ones moved to 7:30. But anyway, as long as that'll disappear at 7, but actually that will disappear at 7. Let me go ahead and just fix that. So if anybody gets kicked out, if you happen to get kicked out, it wouldn't let you back in. So let me edit that. Just take forever, okay. And then we'll go ahead and get rocking. So I'm going to change this to 6:30. And save it, and then if you get kicked out, you'll be able to come back in. Oh, no, it's saying. All right, well, let me know if somebody gets kicked out. Unbelievable. So, so great. So let's get rocking. So here we are in Unit 10. I'm going to kind of go unconventional style here. I just wanted to go out. You've already seen the videos, so I want to show you a few examples and then really set you up for the homework. Let's make this interactive. Fire in any questions that you have. I'll take breaks periodically. But I'll try to answer all these questions from the quiz that I got. But first, here's a couple of questions that I got right off the bat, and this will help you in your homework. So I'm going to go over again what a confidence interval is and what a prediction interval is. Not again, but I'll go over exactly what a confidence interval and a prediction interval are. But you kind of saw that from the videos, so I'll kind of lean on that a little bit. Where am I? So what I wanted to do, I wanted to go to SAS. So let's just go ahead. I'll draw this in the board too, but here is, well, in a nutshell. There's a lot of stuff also I should say on Canvas if you want to download that as I go along. This isn't, the movie data is, and if you want to follow along, I'd open up a SAS window and make a quick data statement out of the movie data here, or you can just watch me do it. It's pretty simple that we've seen before, but this is pretty easy to do. The data, you have the movie data, or the movie data is in the Unit 10 Canvas right now. But that is the movie data that we've been working with for a long time. If I just run good old proc GLM on it, we get this. And by the way, I've updated the homeworks with all the R. We'll kind of go over the R today too, so you should be proficient in doing simple linear regression in SAS and in R, which is a huge skill set. By seeing it by the end of this live session and have done it by the end of the homework. So here it is. All the stuff that we're used to seeing, our ANOVA table, which we'll go over today. We'll go over a little bit of the lack of fit test. We've got our parameter estimate table here, and we have our plots. This blue confidence band, that's what's referred to as a confidence band, and it is a confidence interval for the mean. Remember that the regression line is an estimate of the mean of the normal distributions of Y, the normal distributions of gross, conditional on budget. I'm going to go over and over and over and over and over that again today. But remember that that line is an estimate of the mean of, what's going on here? So time out real quick. I'm seeing some people, is the video problem, you can't see my video, or is the video problem that you can't get on? Oh, it says with the webcam. Okay, it's not important. It's not so important that you get on the webcam. Sorry, I just saw those. As long as you can see my video. But so again, the blue confidence band, there's the mean. I'm pointing to the mean right now. Say X equals budget of 150. That's about the mean. So we're saying that grosses. We're not saying that grosses will have a mean of a little more than 250 million. We're saying that those grosses are assumed to have a normal distribution, and that normal distribution's mean is a little more than 250,000, right? Somewhere around 300,000. Okay, now we're not sure that that estimate, that 300,000 or whatever that specific number is, the one that I'm pointing right there, that's from the sample of only seven movies. So we're not even certain where the mean is. And that mean, so that's what this blue confidence band is. This blue confidence band is saying, hey, we think we're 95% confident that that mean could be anywhere in this blue confidence band. That is the actual, if you put a parentheses right here and a parentheses right there, that would be the confidence interval for that. And then, of course, this dashed line out here is saying that that is the confidence band for a prediction, for a single observation. For the next observation, you could say, I'm 95% confident that the next observation will be no bigger than this and no smaller than that. 95% confident. And I'm going to show you on the board here in a little bit why, how those come about and why those make sense and why the prediction one is always wider than the mean one. It's very intuitive. But for just so that I can have something to refer to a little bit later, if you have a pencil, you might just jot this down. In fact, if you have one or just on your computer or something, just jot these down real quick because they're gonna pop up in the PowerPoint in a minute. So what I would like to do is find the values of those confidence bands. What is the value of this outer region here of this confidence band, and what is the value here? Another question might be, why is it so narrow in the middle and why is it so much wider on the edges? We're going to get to that too. So, so here we go. CLM is confidence limit for the mean. That's what the M is. And that will give you the upper and lower limit that you see from the confidence band. So I run it. The thing is that it only gives it to you for the observations that you have. So notice we had 7 observations to build the regression line, just giving us 7 values of the lower and the upper limit. So let's just look at one here. And the thing that I think is kind of the downside of this is it doesn't give us the budgets. It only gives us the grosses. I remember where it is. So are the, and the R might be a little bit different. But this is the observed, and that's observation 1. And I think observation 4, let's just look at that one for a second. Observation 4, I just know the budget is 35. In fact, I'll show it to you. Observation 4, that's 1, 2, 3, 4. The observed value is 35. I'm sorry, that's the budget. The observed budget is 35. The observed gross is 57. So you'll see that here, but it doesn't say 35. It just says 57. That's the observed gross. The predicted gross is negative 42, and the band is negative 163 to 78. If you would just quickly jot that down, I'd write down budget 35, gross 57. You could say predicted or y hat negative 42. And then lower confidence for the mean, LCM, is negative 163. And upper confidence for the M, UCM, is 78. We just need those values along with the budget of 35. Those are going to come up a lot in our PowerPoint. So I just wanted to remember where those come from. So this is from CLM, again, 57, negative 42, 99, negative 163. If you're not done getting those down yet, I'll come back to them in just a second. I just want to, actually, if I can just squeeze it on here. Actually, that's good. So that's what we're saying here is that at 35, which is way down here, that's the smallest observation I have. That's the first one. My value is a little bit less than 0. That's at negative 42. That negative 42 is the predicted value. The observed value, of course, was higher than that, positive 57. The upper limit of the confidence band is 78. That's this blue edge right there. And the lower limit of the confidence limit was negative 168. That's that lower edge. Okay, great. So a question that will come up is, what if, which is very reasonable, what if I want to interpolate? What if I have a movie that has a budget of, say, 95,000? Let's say I have a budget that has a movie that has a budget of 95,000, and I would like to get a 95% confidence interval for the mean, a 95% confidence interval for the mean gross at that level, at $95 million for a budget. It's not one of my observations, so it's not going to here. So all you have to do is come over here, type in 95 dot, or whatever. A dot is SAS's notation for a missing numerical continuous value, or really just numerical value. So 95 dot, rerun this guy, and notice it's not going to tell us the 95, but it is going to give us the dot, and it's very easy to see that that's the dot. So if you would, go ahead and copy those down too. So for a budget of 95, the predicted is 165, and the lower and upper confidence limits are 83 to 247. So it's a little bit of just kind of jotting down in the beginning, but it's going to help in the end. So again, for budget of 95, we've got the predicted of 165, lower 83, upper 247. Awesome. Okay, fantastic. So that is, and you can do multiples, right? You can do 108 here if you wanted, and do a dot, and you could have a whole, as many as you want in there. You just kind of got to keep straight of where they are in the data set. So now I've got 2 of them. I can do it as many as I want. We're going to use that into this semester and next semester. But very easy how to get that. Awesome. That will, again, help out a lot with the homework. So let's go ahead and stop sharing. Come back over. And again, fire off any questions as you see them, but we're going to go ahead and get pretty heavy into it. So let's go back over those assumptions since they're super important. The regression line, this graph here really tells it all. The regression line, you can think of this as gross, and you can think of these as budget. It's simply the estimate of the mean of those normal distributions for subpopulations of X. I'm going to get deeper into it here. So for this one, for the study hours, we're estimating normal distributions, and that line is estimating the mean of those normal distributions. This line is estimating the mean of those points given a price. So let's look at that again a little bit deeper. This was the basketball data that we looked at with the prices. So we've got the price here in millions and the points over here. So if I looked at that, I'd say that's my best. Maybe I need some better PowerPoint skills. I was pretty proud of that in the first, but maybe I need to make those transparent. But anyhow, these are trying to show normal distributions for fixed prices. These are normal distributions of points. So we've got these normal distributions, and that line is estimating the mean of those normal distributions. Notice also that those normal distributions have the same standard deviation, assuming. That'll come up here in just a second. So that's this piece. The means of the subpopulations fall in a straight line. What I was trying to show with the earlier one was that there are that's the first assumption, there's normal distributions of the response for subpopulations of X, and that the means of those lie on a straight line. And here comes the subpopulation standard deviations are all equal. So notice that these all have the same standard deviation. That is an assumption. There should be another normal distribution right about here. That should be another normal distribution. I guess it didn't make it. And finally, we're assuming that that all the observations are independent. You might say there is an NBA salary cap, so many of the points can many points can be scored in a game. There is an NBA salary cap, and only so many points can be scored in a game. You might argue against independence here, but we'll assume for the rest of the semester that we're just dealing with independence. We'll hit dependence next semester. So here's our movie budget. That's the one I showed you before. Just showed you how to put 95 in there. These PowerPoints are out there. So we're looking at our assumptions. We're for this particular data set, we're saying, linearity, there's only 7 observations. And we're really heavily dependent on this guy. He's pretty influential. Because we saw earlier, if we took him away, the regression line loses a lot of its slope, and it becomes insignificant. So that point is significant, but it's not, doesn't mean we should erase it. So it's questionable, but we'll proceed. There's not really strong evidence for or against normality here. We only have 7 observations, so we'll make that, to continue with simple linear regression, you have to make that strong assumption. Equal FD, tough to tell with such small sample size. We'll assume the standard deviations are the same. Independence, we'll assume independence. With small sample size, you have to really make a leap of faith. But this is just a toy example. Appears to be an influential point. That's something that you would definitely want to report in any analysis. And you may want to run the regression with it, without it. We're going to really get into these. We've seen the residual plots. This is common output for proc reg. Just as a note, and you'll see this in a lot of my sample code, if you use proc GLM, all you got to do to get this nice plot here, if you use proc GLM, is to put on the edge here, plots equals all. PLOTS equals all, if you want this plot to come out of proc GLM. So you'll see that a lot, though. You'll get really used to that. This one here is the residual plot. We're going to cover these other plots a little bit later, but just know for now that these assumptions here are checked with these three right here. So these assumptions can be reduced to the fact that these should be a random cloud around 0, which they're not here, but we only have 7 observations. These kind of look like they go down and then back up, but if we took more observations, we might expect them to balance out if the assumptions are met. This is a QQ plot, which we've covered before. This is a QQ plot for the residuals. If these are met, then this should be a random cloud around 0. This should be, the residuals should be normally distributed. This is a histogram of the residuals. They should have a normal distribution. That's what this thing is showing. Of course, we only have 7, so we're looking for evidence against the normal distribution here, and we don't see much evidence against it. I wouldn't be surprised to see this histogram with only 7 observations from a normal distribution. So again, we're just going to touch on these 3 right now. Next, in Unit 11 is when we hit Chapter 8, which is talking about the assumptions. So we'll really hit that one a lot more. And in fact, in next semester is when we'll really dive into what these guys are. I just want to give you an idea quickly of what they are. These are residual plots, and this guy right here is a Cook. See that point right there? That is corresponding to this point here that has so much influence. Cook's D is a measure of influence. The rest of them I'll leave till Chapter 11. But cool. Okay. So we're kind of scattering around, but now what we'd like to do is get into it. So here is the movie data, which we're really going to look at this with. We know how to get the parameter estimate table. We're looking at the residual plot here. So we can get the regression equation. We're very comfortable with that. There is our intercept, and there's our slope. And the slope is significant, so we decided to use a regression line. We're assuming all the assumptions. Let's get at what we're talking about. So we can have a predicted gross for Y of 40. Just plug in 40. Our estimate is negative 25 million. Not a good look. But how do we do this with SAS? We know how to do it with SAS. You've done it for the last 2 weeks. So there it is. No big surprise. There's proc GLM. Again, if you put a plot equals all here, you'll get that 3 by 3 plot. This comes standard, but you get the same. The parameter estimate tables are the same. The ANOVA table will be the same. Right. Awesome. We want to be experts at interpreting these and feel very comfortable about each number means. Please fire away any questions if you've got them as we're going. But that's it for now. So here is R. This might be your first look at the R. Part of what I'd like for you guys to do is just to kind of reverse engineer this, get into a group. You should be able, it's very straightforward. Given what you kind of know about R already, you should be able to follow this code. This is for the movie data. All you're going to do is substitute movie here and import a different file into R and then make these same function calls. You're going to have to change some of these functions. This is the Y-lim. The Y-lim is your range on the Y-axis. Your X-lim is the range on the X-axis. Of course, your scales are going to change based on what data you're dealing with. So I'll trust that everybody can kind of change the zoom of your plot. But this is how you are a lot of flexibility. And that's how you can do the plotting. This MyLim right here, you can call it whatever you want, but LM is the function. That's linear model. That's the response, tilde. That is the variable. And then, of course, you have to tell it what movie, what data to go and get the data with, or what what data set to do the regression from. And I'll let you play with these guys. The best way to learn is with playing with it. I put this data out there already. You can run it. If you need some help, let me know if you need some help in how to import this. But really try it first or ask around first. It's pretty straightforward. And that's that. This is how you get the prediction intervals. This is for the confidence intervals. This one's for the prediction intervals. So we can make these plots just like that. Notice that -164 and 3. The way that you get these guys is by doing summary after you've done the regression and stored it into something called MyLM. You just do a summary of it, summary MyLM, and it gives you the parameter estimate table. It also gives you the R-squared and the other fit statistics. But I put it up for the regression estimates. Notice 164, 3.4. Notice those are the same as they are in SAS, -164, 3.4. Everything you are, and in fact, it's going to turn out that we can do calibration intervals in R that we can't do in SAS unless we program it ourselves. Cool. So again, I'm not going over this a whole bunch. If you have questions, I'll be around on Sunday. But part of the exercise is to really kind of learn how to take this framework and make it work in R. But it's pretty straightforward if you take it. Cool. All right, so let's dive into confidence intervals. So the confidence interval, again, is represented by this blue band. And the SE, this is talking about the standard error of mu hat. Mu hat is the line, right? So the standard error of mu hat is sigma hat, which is just the same old, same old. Sigma hat here is the square root of the MSE from the ANOVA table. Let's say that one more time. Remember the ANOVA table. Remember the MSE from the ANOVA table. Take the square root of that, and that is your estimate of sigma hat. And notice that it's the square root of 1 over n, that's just the sample size, plus this guy. Mathematically, it reduces to x naught minus x bar squared divided by essentially a function of the the variance of the x's. So that's just n minus 1 times the variance of the x's. This is a typo from the book. I've fixed that in a couple of versions of this. This is n minus 2, not n equals 2. I think you'll see that in the book as well. This could be very confusing. This is degrees of freedom equals n minus 2, not n equals 2. I was just copy and pasting from the book. So, okay. So what we're looking at here is why this confidence band gets narrow and why it gets wider. So what I'd like you to do is think about this. Given this function right here, remembering that a confidence interval is an estimate, which is the line, plus or minus a multiplier, let's just say 1.96. It's a little bit bigger than that because we only have 7 observations, but let's just say it's a multiplier, 1.96, times the standard error. So if the standard error gets smaller, then we get narrower here. If the standard error gets bigger, then we get wider. Let me ask you this. Given this function here, and you can just say it or type it into the chat window, given that function, let's say that right here is the narrowest the confidence band gets, which means that's the most confident I am that the estimated mean is within the narrowest bounds. What x value is that? Not numerically, but what value is represented when the confidence band for the mean is the narrowest? For what x is that true?
It's just the mean of the samples.
Bam! Exactly. That part right there, if I'm pointing to it, is x bar. And you can see this x naught is where I am on the x-axis. So when x naught is x bar, then the mean, notice what it reduces to. When x naught is x bar, that as x bar minus x bar, this whole term here becomes 0. And I'm just left with sigma times the square root of 1 over n, which should sound super familiar, right? That's just the standard error of the mean. And we know that every regression line, every regression line goes through the point x bar, y bar. Every regression line goes through the point x bar, y bar. And at that point is the narrowest the confidence interval for the mean will get, and the estimate of the standard error of y hat is simply sigma over the square root of n. It's simply sigma over the square root of n. Isn't that's amazing, right? And that's what it is. And when you get, the further you get away from that, the further I get away from X bar, right, the bigger this term gets, which means the bigger the standard error gets, which means that's why it's getting larger and larger and larger as I get farther away from X bar in both directions, because it's squared. Okay, that's one of the big stopping points there. So let me know if anybody's got any questions. But that's a big piece. Now another question is going to be, I want you to think about till we get there. This dash line, is the dash line bent or is the dash line straight? Don't answer that yet. But that's one question I would like you to think about. Because clearly the confidence interval is bent, and it's because of that. Okay, awesome. So we're doing good. So let's look more at confidence intervals here, knocking it down. We know that's the standard error. What you're going to do in the homework is you're really going to be comfortable with these formulas and what they're doing, and you'll actually do it in Excel. So kind of by hand, but I would recommend Excel. I've put some links to videos out there. I think they're in this PowerPoint. If you get kind of questions on how to do that. But what we're going to do is use these formulas to actually build these confidence intervals. This will probably be the only time in your education that you do this, and forever then from then on, the idea from my point of view is you will have the idea, you've done it before, you'll kind of have earned the right to have the computer do it for you at that point. You'll know where each number comes from, you'll know exactly what SAS is doing to get there, and so really kind of recognize this, I think, as a landmark in your education on this, because it's probably the only time that you'll spend this much time really looking under the hood. You'll just use SAS or R or something to do that later. Again, that's a minus sign there. Need to fix that. Okay. So notice here that the way I've done it, I'm going to take you out and show you that here in just a second. But so here's the budget of 35. These are the numbers. That's why I had you write them down. Those are the numbers that we found before. But this was me actually finding them in SAS. Right? Those should have been the numbers that you wrote down before. And then these numbers as well, right? I put in 95. These are the numbers that we had written down for those. You probably didn't have the standard error. It didn't give us the standard error. I know it gave us the predicted value and the lower and the upper bounds. Those are the ones that we were looking for. Okay, and in fact, so right now I'm going to take us out there to show us that this is already in Canvas. I have the one for the movie data, so share my screen. There's just a bunch of information today, which is as usual, but I mean, we're really growing statisticians in this case. So where am I? I am right here. So here is the data set that's on Canvas. I just want to kind of take you through this. I really think this is kind of cool too. All we're given is 7 data points, right? 7 budgets and 7 grosses, corresponding grosses. And from that, we can generate much more than this. But look at all of the analysis that we can generate just from those 7 numbers. Of course, we have to make the assumptions. But here is X and Y. X is the budget. Y is the gross. From all of those, we know from previous chapters that beta 1 is simply this X bar, Y minus Y bars divided by the sum of the X minus X bars squared. That was from that calculus. But that's just the formula for beta 1. I'm going to give you another formula here in just a moment too. But so notice what these are is when you go through this, you can always just click on something and click into the formula bar, and you can see that this is simply X minus the mean of the X's squared. That's all this cell is. And that's 62 minus 89 squared. This guy here, I go down to 35. I look at this guy, that's them too. It's just 35 minus X bar. So you're going to, basically. Great. This is the same thing. This is just Y minus Y bar squared. And notice this guy is X minus X, not squared, X minus X times Y 65 minus Y bar, 146. And you do that, notice, for all 7 observations, add them up. So when we look at beta 1 here, Beta 1 is just the sum of the x minus x bars, y minus y bars, divided by the sum of the x minus x bars squared. That's all beta 1 is. That's all beta 1 is. And notice that beta 1 is very familiar. We've kind of memorized this one by now. It's 3.47. And beta naught, you can see beta naught here. This is the formula beta naught. It's just y bar. X bar minus, that's y bar. Y bar minus K9, which is the slope. So you got to find the slope first, but it's just y bar minus these, getting these from those formulas. So you guys out. Notice that's minus 164. Taking us through a little bit more of this. Again, I have a nice long video, or not long, but probably 10 or 15 minutes, I think, on how to do this. So I take you through it. So I won't have time on it. I want to show it to you. I'll take you through this piece right here. You're going to see these in the slides too. This right here, the sample SD of X, notice that that's just the standard deviation, the sample standard deviation of E4 to E10, which is X's. That's just the sample standard deviation of X. Notice that what I'm doing here, this is the estimated Y for X equals 62. The observed was 65, but my mu hat, the regression, 62 into the regression equation. So I'll show you that right there. And you can see that. That's just beta naught, which is K11, beta naught plus beta 1 times X. Right? That's all a simple regression equation is. I am not sure what that is. We might want to investigate mute though. That is the intercept. Once again, that's the intercept plus beta 1 times X. That gives you this guy. That's the estimated value. You get the estimated values for all of them. If I have the estimated value, remember what residual, the estimated value minus the actual value, the estimated value minus the actual value, and you take the residual squared, and here we go. That's the residual squared. Add up the residuals. That's the error. That's the sum of the squared residuals. That's the MSE line. You might write that line down too if you would. Yeah, this will be great. If you would write down 35,362.6, and remember, maybe write down to the side of that, SSE. That is the sum of the squared error, the sum of the squared residuals. And of course, if we divide that by n minus 2, n being 7, notice up here that dividing that by 5 and square root, basically I get sigma hat. Yeah, I probably shouldn't put the square root there. This is really, shoot, I probably shouldn't have that on there. The MSE, I should probably just take this off. Here, we'll do this. I just noticed that. This is really the RMSE. So be sure to write down that 35,362.6. If we divide that by 5, you'll get the MSE, and this guy up here is the RMSE. So the RMSE is sigma hat. That's the sigma hat that I'm using. So anyhow, it'll take you a little while to get through all these, but notice this right here. This is SE beta 1, and this is SE beta naught. Those are what we used last time. And those are functions. That's just sigma hat times the square root of this function right here. So I'll let everybody kind of run through that. It'll take a while to go through this, but and I can help you out on Sunday after you had a chance to look at it. It's pretty tedious, but I think in the end it usually helps everybody really see what's going on with these equations. Notice down here is me doing, these are the same ones you'll see in the PowerPoint. This is just me doing the confidence intervals. This is saying the confidence, that's for that blue band. Notice that's the red band here. So if I highlight it, that's the upper bound. Notice how it gets highlighted over here. This guy here, that red one, is the lower bound. And then notice here are the prediction intervals. So the prediction interval, I highlight the blue one. So that's the lower limit of the prediction intervals. That's the upper limit of the prediction intervals. You'll solve all of those by hand using Excel. It's actually kind of fun. And then we can also do the calibration intervals down here that we'll get to. Let me stop here.
Are you going to upload this one to the Canvas?
That's on. That should be on Canvas right now. Yes.
Okay.
Yeah. It's like chapter something. What is it called? It's called Lecture 15 and 16 correlation, because it's from my campus class. It's a lecture from campus, but yeah, that's what it's called. Cool. So any questions so far? Look at confidence intervals. Got a little bit of an idea of what they mean. I want to do a little chalk talk here, but this is kind of on the climb up the mountain. We're kind of at a little stopping point. So you grab some water, have a little sip of tea.
Mm-hmm. Professor, so
yes,
the confidence interval then is based on the mean, and the prediction interval is based on what, a statistic? I'm trying to figure out, one is the parameter and the other one's a statistic? So the confidence interval is based on a parameter?
The confidence interval is an interval. They're both calculated from the data, from statistics, but they're both giving you inference about a parameter, about an unknown value.
Population. Got it.
Mm-hmm. That's right, from the population. So, okay. So here's what I want to do is quickly give you my little spiel on exactly what Max was just talking about. And that is, let's do this. So let's call this Y. Let's call that X, pretty natural. And let's say that that is mu hat. That is my estimate. So this line is estimating mu hat Y given X. And as soon as you get that idea that that's what this is doing, things go pretty smooth. So there's a normal distribution here. There's a normal distribution here. There's a normal distribution here. And all of these have the same standard deviation. Now, what we're saying is, given our formula, is we would like to, so let's take this guy right here. Right, let's call that 3. That guy right there is mu hat of Y given X equals 3. Right, that's 1, 2, 3, 4, 5. We're assuming a normal distribution of Y's given X equals 3. But that's an estimate, right? It's got a little hat on it. So they must have some uncertainty tied to that. And we know that that uncertainty, let's build a confidence interval for that. We know that that uncertainty is, where should I put this? Let's build a 95% confidence interval. So that 95% confidence interval is mu hat plus or minus, I'll just say that that's for this guy here, that's mu hat plus or minus T, let's call that 0.975 with 5 degrees of freedom. Right, that's my multiplier. This is for 95% confidence interval. I'm going to split it alpha over 2 and use 5 degrees of freedom times the square root, times sigma hat times the square root of 1 over n plus the sum of x naught minus x bar, and actually I know x naught here, times the sum of, actually not even the sum, just x3 minus x bar, which I'll just write it as x bar squared divided by I put 5 here because I assume my sample size was 7. I'll just go ahead and assume my sample size was 7. So that'll be, that's really 1 over 7. This is n minus 1, so that's 6 times sx squared. So I can see how don't let that get confusing to you. That's just the variance of all the x's. That's just the x bar of all 7 of those x's. It's just saying that that's n minus 2, and I'm saying that I had 7 observations. My point here being is that this right here, what this is going to give me, this plus or minus, is going to give me a lower bound, and it's going to give me an upper bound, because I'm doing plus is going to be the upper bound, and minus is going to be the lower bound, and that is what the confidence band represents. The lower bound here, I'm saying this guy, I don't know that that's the real estimate. I think that estimate could be as low as this, or it could be as high as this. And that is the lower bound, and this is the upper bound. Let me stop there for a second. That is what we're finding here. We can take mu hat, which I'm saying is the same thing as this in shorthand, plus or minus some multiplier, times the standard error of mu hat, which is this guy here, and that's plus or minus is going to give me a lower bound and upper bound, and that's exactly what's represented by that confidence band right there. And if I change x to 4 or x to 5, that'll become a 4, and that'll become a 5. That'll stay the same, that'll stay the same, that'll stay the same, and this will get a little bit bigger, which makes that wider, which makes that wider, which makes that wider. So that's all we've explained right now. To Max's question, which is where I want to head next, is what about if I don't want inference just for the mean, but I want inference for the next observation? So let me make a quick note over here. This is awesome. This is awesome when it all comes together. So don't let me get too far ahead. If you have a question, guaranteed somebody has probably more questions. But if not, then I'll just keep rolling. So here's the idea. Now what I want to do is let's go for x equals 3. For x equals 3, this is an estimate of the mean. So if I took another group of 7, if I took another sample of 7, I wouldn't expect the mean to be estimated to be right there. It might be a little bit higher, it might be a little bit lower, just from any other sample that we have. This regression line is going to move around a little bit. So, so this is saying, well, I'm 95% confident that the true mu, not mu hat, I'm 95% that the true mu is contained by this interval, which means it could be way up here or it could be way down there. So let's draw this. For x equals 3, so let's do that. That's a hat. So important. This little piece right here is really awesome if you can own it. So I'm saying right now that this is for x equals 3. For x, so I'm saying, hey, give me that slice. That normal distribution right there is that normal distribution right there. Remember that this is that mu hat right there is that guy right there. That dot is that dot. But now I don't want to know where the mean is. In fact, let's stay there for a second. So I'm going to make this bound and this bound. Let's say that this bound is my lower bound and that this bound on the equal side is my upper bound. So what does that mean? I think that my best guess is that the y's are normally distributed. Right? This is the distribution of y's. My best guess is the y's are normally distributed with mean mu and standard deviation sigma hat. That's my best guess. But I'm not sure that mu hat is where it is. So now what is here. I think it could be as small as here. It could be as big as there. And what I really would like to do right now is say, hey, I'm going to take one more pull. I'm going to take draw 8. Where did draw 8 come from? I mean, what is draw 8 going to be? And you might say, I'm 95% confident it's in here. But the next draw will be here because this is the distribution of y. And you would be right if I knew that this was mu hat. Or if I knew that this was mu. I would be right if I knew that was mu, but I don't. I'm uncertain about it. So I'm going to draw another distribution, giving the biggest case. The distribution of y's might be centered at the upper bound, right? Because we said mu hat might be as big as this. And mu hat might be as small as that. So this is the lowest scenario. I'm trying to draw all those distributions, and I did a decent job, with the same sigma. They're supposed to all have the same sigma. So now my question is, where is the next one going to be? If this is the mu hat, I'm 95% confident that my next observation is going to be here. But what if mu hat is really here? then I'm 95% confident that my next observation will be here. So I'm going to record that. The biggest I think it could be would be here. And again, that's the next observation, not the mean of a bunch of observations, just the next observation. So then, what about the worst case scenario? Because I think mu hat could be as small as here. So if that's the case, it looks like I'm 95% confident if this is the distribution that my next pole would be within this range. So that says, okay, well this one looks like it could be as small as down here. So check it out. This is my confidence interval for mu. This is my prediction interval for y. And notice that the prediction interval is wider than the confidence interval. And that's why. Because we not only do we not sure, if you tell me where mu is, I still don't know where y is. And now I'm telling you, I don't even know where mu is. So I'm going to say mu can move around here, and if that's true, then as mu's moving around from here to here, y could get as small as here, and y could easily get as big as there with 95% confidence. And that's what this line represents here, is that is that dashed line that you see on the test plot. For the mean, the dashed lines are the prediction. Okay. But wait, there's more. Let's go ahead and use this space up here. So how do I find those prediction intervals? And the PowerPoint will go much faster once we have this. But how do I find, for x equals 3, I'm 95% confident that the mean is contained in this interval. If I took one more observation at x equals 3, I'm 95% confident it would be contained by this bound right here. But how do I find that interval? Isn't there a formula like I put over here? Isn't there a formula like that that will give me that prediction interval? And yes, there is. The only thing that's going to change is that piece right there, is the standard error. So here it comes. So we're going to do this. So this is the standard error of the prediction of y, we'll say, of y given x equals, we'll just say x, of y given x. So the standard error of the prediction of y given x, and that's equal to, and here it comes. I'll just kind of, I'm going to do it quick here once we get rolling. It's got two pieces. The standard error says I don't know where the mean is, and after I don't know where the mean is, I don't know where the y is. Notice that the standard deviation of each of these is sigma hat. So all it is, all this is telling us right here is that the best estimate of my prediction is the mean. If you're saying, hey, where's your next y going to be? My best estimate is mu hat. It's still the mean. But my the standard error to build this confidence interval is going to be the same standard error of this guy plus the uncertainty that I don't know. Once I think I know where this guy is, I still have an uncertainty. So all this guy is the square root of sigma hat squared plus the standard error of mu hat of y given x squared. Let that sink in for just a second. To make it more intuitive, I should have probably switched it. But all this is saying, hey, the standard error of the prediction of y given x is just the same standard error as the mean, plus the uncertainty that once I know where the mean is, I still don't know where the next observation is. It's simply adding them together. You got to square them to make them variances, and then take the square root once you're done. And you can see that if this is the standard error, this standard error here is the same as the one that we put down here. That's this one. You know that this is positive. You know that that's positive. So this will always be bigger. If this is always bigger, that means that the prediction interval will always be wider. so it all fits together. That's the standard error of the mean. That's the additional sampling error. That's the additional error uncertainty that once I know where the mean is, I still don't know where the next observation is. That's my estimate of that. Take the square root. I've got my estimate of this guy. So my prediction interval is mu hat of y given x plus or minus some t multiplier, I'll say. That's my multiplier, times the standard error of the prediction of y given x. And that's it. It's the same center. That's the best estimate of the mean. That's the best estimate of my next observation. The multiplier will be the same, but the standard error is bigger. And if the standard error is bigger, the confidence interval is wider. And that's all I got to say about that. That's a big step for us. Does anybody have questions on that? That's our next big stopping point. So just as kind of a concept check, you should, at this point, if there's no questions, you should have a good idea of A, what a confidence interval and a prediction interval are. This one is an interval for the mean, that one's an interval for the next observation. You should also have a good idea as to why, intuitively, why this one is smaller than that one. And then mathematically, you should have a good idea of why this one is smaller than that one. And it all comes down to that standard error. And that's the whole point. So if you've got all that, then you've got what I intended you to get. Inevitably, sometimes it takes sleeping on it. I get it. We can come back on Sunday and talk about it more. But I'd love for everybody to have that concept down pat. Cool. All right. Well, then let's get back to it. Here we go. Right there. Okay, great. So that's all this function in it for all of those guys. So that's going to be a fun exercise. Let's just kind of hear these guys and interpret it. So here is the interpretation. The whole point here is that this is a confidence interval for the mean. So we're saying, well, 95.
Professor can't hear you. Lost the sound.
You can't hear me? Hello, hello?
Yeah, now we can hear.
You're back.
All right, sorry. You can hear me now for sure, though? How long ago was that? Uh-oh, now I can't hear you.
We were not able to hear you for about like 15, 20 seconds.
Okay. Can you interpret this one?
Actually, when you started this thing, then we lost audio.
Okay. So the whole, you probably get it, just is that when you're interpreting the confidence interval, when you're interpreting that band, we're talking about the mean gross. And if we change the budget, then we're talking about still the mean gross. It just gets a little wider. When we talk about the prediction interval, the only thing that's going to be different is we're going to lose the mean because we're not making inference about the mean. We're making about an individual movie, not the mean of 7 movies, the mean of the sample size of that many movies. So let's check it out. Okay, so at 200, so let's say that I'm at 200, this Excel estimates, we can get these from SAS, of course. You can see the 332 to 727. Okay, and this is just me showing you how to do it in SAS. You're just doing CLM, just like I showed you. And that's exactly what we showed at the beginning of class. You should be able to get these pretty quickly. 332, there it is, 327. Great. That's just from the beginning of class. But what if, let me remember what I was about to show you here. Okay, so this is PROC-REG. Okay, I'm sorry. So this is actually important to see which way you go. That was from the one that I did before. This one's from PROC-REG. It's the same information, just a slightly different case. Notice that it gives you the standard, right? There it is. That's the standard error. And notice that the standard error changes. And that should be no surprise, right? Of course the standard error changes. That's what makes the confidence band get narrower and wider. So notice that that's a really big standard error. Notice that that's a really small standard error. That's because this one is closer and this one's farther from X plus. And then there are the lower and upper confidence limits of the mean. Great. So it's just the two different ways to look at it. We're still in confidence intervals here. I like to make a show. So now what would happen, this is what we did before. Again, I said we can just kind of go through these. 95 wasn't enough here, just like I did at the very beginning. And we get the estimate comes out, just like we showed there. Boom, there it is. There's my lower and upper. You copied that one already. Get that reg or in prog GLM. And there we have it. And so if we wanted to interpret that, it is we are 95% confident that the mean gross when the budget is 95 million is between 83 and 247.9 million. Good inference. Notice the mean there. All right, here's how you do it in R. I'm not going to go over this so much right now. I'll see how much. Here that this interval equals confidence. That's what gives you the confidence interval. If you put predict in here, I'll let you play around with that. So looks like somebody got kicked out. So I'm going to skip through the crickets example here. This one's just in there, so you have another example to look at. But you can play around with that one. But let's go to prediction intervals. So for prediction intervals, this is great. Now we're looking at this dotted line. Remember my question too. You probably already have that idea. It doesn't look like they do, but it doesn't look like they do. But the answer is, of course, they actually do, because that is the prediction interval gets narrower as well. Whatever focuses, the prediction interval gets narrower as well, and that's because of mu hat. And we know that mu hat gets smaller as we get farther away from X bar. The reason why you can't see it so well is because sigma hat squared drowns it out. Sigma hat squared does not get smaller or bigger based on how far X bar is. So when I've got sigma hat squared in there, it changes. The standard error percentage-wise doesn't change as much from X to X because sigma hat squared is staying fixed, and it's as big or bigger than that SE. So I'll let you think about that. But yes, the prediction interval is getting narrower. It just, you can't see it as well because sigma hat squared does not change, and that makes when SE of sigma hat squared changes, it makes a smaller difference in the overall SE. Okay, so that's an important point too. La 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 la. So great, we're making really good progress if everybody's on point. But now, this is what's kind of fun. Now we know what that means, or at least we're pretty familiar with that very formula right there. The standard error of the prediction. The standard error of the prediction is just a function of the standard error. This is just saying I don't know what the mean is, and even once I do know where the mean is, I still don't know where y is. So I'm just going to add those two variances together, and that is a measure of the uncertainty of my prediction. And you can call that the random sampling error, and you can call that the estimation of mu error. And they add together to give you, take the square root and add together to give you the standard error of the prediction. Great. So we've been through that. This is another way of writing it. This right here. It's the same idea. And you can see it right there, right? There it is. This guy here, that the standard error is a function of this difference. The farther we get away from X bar, the smaller it gets. The difference is that this is often much smaller than 1, or in this case, smaller than sigma hat. So that's just reminding us what the standard error of mu hat was. Okay, so what does that mean? We can do those in Excel. So for 200, I can do those in Excel, and that's in that Excel spreadsheet. We can find those using this formula. That's the RMSE. That sigma hat right there is that RMSE I showed you. And that's, of course, just the number 1. That's 1 over n. You're going to have to find this for each value. This value of x minus x bar is going to change, but that'll be good to work through in Excel. So on and so forth. So you can see that guy. This is what it's going to look like, though. Okay, so here is something that is really going to be important for us, is this standard error. I don't like this, but we just got to know what it is. Notice it's standard error of mean predict, even though this is the prediction. This interval, notice, is wider than the interval was before. This interval goes from 237 to 823. The interval for 200 before was much narrower than this. So this is giving us the correct prediction interval. For 200, right, for right here, where is it? 237 should be right about there, right on the dotted line. 237 should be right about there, and 823 should be right about there. That's what those numbers are. But this standard error of mean predict is still the standard error, not of the prediction. It's not this guy. It's just, let me go back to it. It's this guy. So for whatever reason, the standard error that SAS gives us is the standard error of mu hat, not the standard error of the prediction, even when you call for the prediction. And I didn't cover how to call for the prediction. Instead of CLM, you'll notice here that you're using CLI for individual. CLI instead of CLM. And that'll give you this column here. For whatever reason, though, it doesn't give you this. You could find this very easily, right? And you will end up doing this when you do it by hand. But this is just a piece of it. And then you'll have to you'll square this. So you'll end up squaring this guy and adding it to the MSE or the RMSE squared, and then taking the square root of that to get the prediction standard error, to get the prediction standard error. So great. So this is how you do prediction intervals in R. It's the same as the one I showed you before, except it's interval equals C predict here. R is very straightforward and intuitive. You'll have a good idea how to do all those. I've got this code is out on the internet right now, so you can just fit that code to match whatever the next data set is. But it's very right. There's the fitted value. There's the lower. There's the upper. We can see there's the one we just looked at for 200. Same numbers. Awesome. You can do it in SAS. You can do it in R. There's the ones for crickets. I'll let you play around with that one if you want to play around with another one. But all right. Okay, so that's another, I didn't need to do that. So ask any questions right now. This is another little stopping point for us. We're going to hit calibration intervals, and then we'll see how much time we have left. I thought that I should have had, driving me nuts. It's a little delayed.
Professor?
Yes.
Can you please repeat the idea behind why the prediction intervals are straighter than the conference interval?
Or wider?
Why they look more like a straight line?
Oh, because the difference, okay, so yeah, the question is, why do these look straighter than these? And all I have to do to see that is the difference in standard error from here to here is reflected only by the standard error of mu hat. Whereas the difference in standard error from here to here, the standard error of the prediction, is sigma hat squared plus the standard error of mu hat squared. And what I'm saying is so let me show you what that means. let's say this. Let's say mu hat squared. Let's say that that's equal to 10. Let's make this big. You got to get my numbers right here. This won't make any sense. So let's say that, for example, sigma hat squared is equal to 10, and let's say that SE of mu hat of y at x equals 3 is equal to 1. Okay, not so much important that that's smaller or not. But now let's say, so that would mean here that the SE predict, in this case, let's see how I can do this right. Dang it. What does that look like? We need some more room. Somebody erase this. So if these are the case, then the SE predict would be the square root of, did I square that? I'm sorry, I got to really think of my numbers here. But let's say that this sigma hat, let's say this is just sigma hat. Let's say that that's sigma hat, and let's say that it is, say, 3. So this is going to be sigma hat squared from up there, right? Sigma hat squared plus SE mu hat y times x there. So this is going to be squared plus 1 squared, which is going to give us the square root of 10. All right? So that is going to be the standard error at this point right here. And if I do this again, let's say the SE of mu hat for y at x equals, say, 5 is equal to, let's say that that one is a little bit bigger. Let's say that it is 2. So it's doubled, right? The SE at 3 is 1. The SE at 2, at 5 is 2. It's doubled from here to here. It's doubled from 3 to 5. That standard error is doubled from here to here. Got it. So, but now the standard error predicts sigma hat equals 3 is still 3 over here because it doesn't change. It's assumed to be the same. So this SE predict, just to finish it, sounds like you got it, but the SE predict is now equal to the square root of still 3 squared plus 2 squared, which equals the square root of, what, 13. So this one's only got a little bit bigger, whereas this one doubled. So you're going to be able to see a huge change when something doubles, but this one only got, right, this one got 100% bigger. This one only got, now I'm curious, second square root 13 divided by second square root 10. This one only got 14% bigger. If I divide this by that, it only got 14% bigger. This one got 100% bigger. That's why you don't see as big a change.
Thank you. Makes perfect sense.
Okay, perfect. Awesome. Thank you. Thank you for the question. It's a really good question. Okay, let's hop into it. Calibration intervals. One thing I wanted to say left there, I guess I didn't put that in the PowerPoint. When I'm, the last thing I wanted to say about this is when I'm interpreting this, I can't believe I don't have that in here. I need to add it. I'm saying for the budget of 200, I'm 95% confident that the next gross, not that the mean gross, but for a budget of 200, I'm 95% confident that the gross of that movie, of the next movie, will be contained in the interval 237 million to 823 million. That's the difference in the interpretation of a prediction interval versus the confidence interval for the mean versus the prediction interval for the next observation. I'm sure I have a slide of that coming up here. Okay, so then we did the crickets. In fact, you can see it here when I do the crickets. So here we've got this guy, we're doing parameter estimates. So find a 95% prediction interval. And so notice, hopefully, when I do that, here it is. So we are 95% confident that the temperature, not the mean temperature, right? The Y here is the temperature, not to go through this whole example, but the Y is the temperature. We're 95% confident that the temperature, not the mean temperature, when the observed chirps, the X, are between 1,000 or 1,000 per minute, are between 68 and 999. So there's a different example, but you can see for, again, for 1,000 chirps, I didn't have it in there, so I just put 1,000 dot. And so here it outputs right here. The prediction interval is from 68 to 90, and that's where that came from. But notice it's not mean temperature. That's what it would be for the confidence interval. It's just temperature for the prediction interval. Okay, last but not least, which was a generation of a lot of questions in the quiz, first thing I want to say is that this generated a lot of questions in all the classes. I actually got questions from the other instructors' class too about calibration intervals. It is by no means is this the focus of this chapter. So the big intervals, prediction intervals, the ones you're going to be working with most of the time. But it's not important. But this is a small piece of the chapter. So don't think if you don't totally understand calibration intervals that you've lost it all. You actually have most everything. And to be honest, calibration intervals are not handled very well or very consistently with our analytical methods that we have to present in this chapter. They're not going to match R exactly, and they're not going to match the visual method that we recommend as well. But the idea behind it is very simple. All we're saying here is, or the equations that you saw in Dr. McGee's videos. All we're saying here is that potentially what we want to do is do a reverse regression. Essentially, is we want to say, given some value of gross, can we get some estimate of what we should set our budget to be? And all we're going to do is here is say, hey, well, let's say we want a gross. If I would like our movie to gross, I forgot what I had here, 240 million or something. Let's see what I have here, 210 million. So if I want to say, if I want a gross of 210 million, what should I calibrate my budget to be? Because calibration is something that you can do. They got this from, because they used to use these in industry for machines, for like temperatures or pressure. And they'd say, well, we want our phone. What's that?
We use them in manufacturing to establish upper and lower limits and tolerance to make sure that machines are running as they ought to be running.
Great. So it sounds, yeah. So Max, do you deal with calibration intervals?
I have. I used to 20-something years ago for Pepsi-Cola in the bottling plants. We had to calibrate them because as you're putting fluid into a bottle, you had to make sure that they didn't overflow and they couldn't go underneath. And there were tolerances that we had to hit on both an upper and a lower limit. And we had to calibrate it, and we would run those upper and lower limits to make sure that things didn't go out of sync. If they went out of sync, then we'd have to shut down the line and put maintenance and make sure that they hit those tolerances.
Man, that is awesome. That is super cool. Are you? Who all is coming to the immersion? Just a show of hands, I guess. Cool. Awesome. Well, I should see you guys there. Yeah, those are the kind of conversations I'd love to have when you guys come in for that. I love generating more examples and really kind of getting together and have synergy ideas. Awesome. So here is so just an example of how to find those calibration intervals. But again, through the visual method here, it's very quick, but not necessarily super accurate. I'm going to give you an analytical method from the book, but if you read even in the book, it's less accurate. You can see that even here, the calibration interval isn't symmetric, right? My best. Notice that this is much closer together than this is to here, right? So from here to the center of the interval, center quotation marks, is much different than there, and that gets worse as the regression line gets flatter. That gets worse as the regression line gets flatter. As the regression line, as the slope gets more increased, that happens that happens less. Or that's, you can see if it was completely vertical, which is impossible, but if it was completely vertical, then it would be symmetric. Anyhow, you're going to fix it at 210, and at 210 here, you can see what the estimate is of the mean. This would be a calibration interval for the mean, and you just backtrack those from the limits down. That is, about 80 million. You could make you could make a plot more accurate if you wanted to. This was estimated to be about 157 million. So actual, so this is, I'm saying mean versus the prediction. So for the mean, I'm just going to do the same thing, but I'm going to do it on the prediction interval. So 210, I'm going to take the limits. I'm going to say, hey, well, what was the biggest prediction interval that gave me 210, and what was the smallest prediction limit that gave me 210, and that will be my calibration interval for the actual, for the next one. I say actual, it's for the next observation. So this one is, of course, wider, 25 million to 200 million. So, okay, so just to get there, this is from the book, what's kind of recommended as an approximation. So let's just kind of go through those. Dr. McGee gives a separate, Dr. McGee gives a different formula in the videos. And then also, this was the first time I had R do it. And when I looked up the documentation for R, I've just got this book. I just had one of it's this old book from 1983. So I got this book. It gave a reference in this book from 1983. So I'm still investigating on how R does it, but it's different. All four of these methods will give you slightly different calibration. All models are wrong. These are all approximations of the same idea. But this will make somewhat of sense. So this is the standard error X hat. X hat is like Y hat, but it's for the reverse. So it's I give you a Y, X hat is the best prediction of the X that's going to generate that Y. And so, of course, this will be the standard error of that X hat is the standard error of mu hat divided by the absolute value of the slope. And X hat is exactly what you'd think it'd be. You're just going to solve the regression equation for X. And in solving, so we've got the estimate, we've got the standard error, there's our confidence interval. It's just the estimate plus or minus the same multiplier times the standard error. Very easy to calculate in Excel and in R. So we're going to do it by hand here. So let's say that I wanted a calibration interval. Let me get all these guys and show it. So let's say that I wanted a calibration interval for 166 million. I wanted to see what kind of budget should I expect or should I plan for if I want to generate a movie that is $166 million. At calibration interval, my best estimate is 166. So 166 minus the intercept, which was 163 something, divided by 3.4 something. So that's how we got the, that's how we got the 95. I guess that came out to be close to 95. The T is 2.597 or 2.57. The standard error, so let me save you a lot of time. This standard error, this 31.9718, is the standard error of that guy. You can get that straight from the that table I was showing you earlier. Remember when I showed you the CLM or the CLI table and it had the standard error, the mean in it? You can get that number directly from there, and that's going to help when you try to do these calibration intervals. And you're going to get it by putting in a budget of 95. And so then this right here, yes, it looks familiar. That's just the slope. And so that's it. It's 95. So I'm going to plug in 166 minus the slope divided by the standard error. I get about 95 plus or minus the T multiplier I look up times SE of mu hat I can get from the CLM or CLI table. That's just the slope. And there's my calibration interval. So we're 95% confident that the estimated budget that would be required to gross a mean of 166 million is between 71 and 119 million dollars. Our best estimate is 95 million. Contrast that with a calibration interval for the prediction interval, not for a mean, but for a prediction. Contrast that, and we have x hat equals y minus beta naught divided by beta 1. It's the same estimate, right? It's going to be 95 is the same estimate, but the prediction is going to be different. So notice that this has a narrow interval, 71 to 118. This one has a wider interval, 28 to 161. And how do we get that? It's because the prediction is the SE prediction divided by beta 1. This one is small. This one is bigger that we covered before. And of course, so this is going to be bigger. And if that's bigger, then it makes our confidence interval wider. And so notice that the only difference in this interpretation is the fact that the mean is gone. Which brings me to my last point, is we are 95% confident that the budget required for a single movie to gross $166 million is between $28 million and $162 million. Our best estimate is $95 million. Notice in order to calculate that, you needed to get SE predict. And remember that SAS isn't going to give you SE predict. You're going to have to calculate it yourself. All that means is you're going to have to do, you can see it, you can remember it, you're going to have to do this calculation. You can get the SE, and if you haven't figured out by Sunday, I'll show it to you. But work together to get it. This SAS will give you this one. The ANOVA table will give you that one. And then so you're just going to add those, square them. Notice you got to square them, add them together, take the square root, and you'll get that 81. All right, you'll get that. So that was a lot of kind of what to do without showing you, but use those formulas and you'll get this 81.
Professor, I couldn't hear the last 10 seconds. When you went up to the board, you cut out. You said SAS will give you this, and then it went.
Okay. So to find that prediction interval, right? The 81 that I just showed you on that PowerPoint, I'll show you again here in just a second. To find the standard error of the prediction, you're going to have to get sigma hat squared and add it to the SE of mu hat, and remember to square it. That's where the common mistakes are not squaring it. SAS will give you this. SAS will give you that. The ANOVA table will give you that. Add them together, take the square root, and you'll be able to get this number right somewhere. It will be right here. This is 81. This is 81.197. In fact, let me show that to you real quick. Well, we got another couple of seconds. I think this will save you a lot of time in the homework. Let me just show you how that comes about. If you want to bust out a calculator or get an Excel screen up or something, this will help. So how to get that number right there? Let's just say I was trying to figure it out. Let's just go out to SAS here. So notice that here's my 95, right? We said, hey, we wanted the standard error for a budget of 95. We're trying to do this for that prediction interval. I mean, for the calibration interval, but for an individual. So what we did at first is we said, hey, what is the best estimate for 166? And I plugged it in and I got, hey, the best budget estimate for 166 was 95. So what I'm going to do is put these in here. Notice I have CLM. That's going to give me that 30, the standard error of mu hat. Where is it? Oh, so actually, I forgot about that. So GLM doesn't give you the standard error, so that'll save you some time too. Notice GLM does not give you the standard error. So if you do that, I want that standard error of mu hat so I can make these calculations. So I'm going to come over here. I'm going to see if CLI gives it to me, but I doubt that it will. So if I do the prediction intervals here, yeah, notice CLI. So I forgot about that. So proc GLM won't give it to you, but if I make this proc reg here, and CLI will give it to me too, but just to be clear, I'll make it CLM. So if I do that, hold on, I made a, sorry. So when you change it, I forgot, solution is not a word that goes with proc reg. So if we change that, notice now that this guy here, so notice that's for 95, if you remember, that's the first one that was missing. The standard error is 31.97. Luckily, I have this sitting right here. This is the PowerPoint. Get to the calibration intervals. So there's 31.97, right? That's where that number comes from. You can easily calculate that just by doing that. 31.97 comes from, you can get that directly from this table, 31.97. But the question would be, well, what happens when you're asked to do a calibration interval for an individual? That's 89.971. How in the heck do I get that? And the way you're going to get that is by getting the sigma hat squared plus that 31 number squared, and then take the square root of that. So what I'd like you to do is, here is the ANOVA table, right? There's that ANOVA table. Remember from the very first thing that we did in class today, one of the very first things, I asked you to write down the SSE from the Excel table. There it is right there, right? 35.36, probably 2.6, but that's the number that I asked you to write down from the Excel table. And then if you divide that by 5, you get this guy. And then remember from the Excel table, I called it RMSE. It's this 84.09. So notice, to get that 80, whatever that is, to get that 89.971, if you want to do it, all you're going to do is this. We know that 84 squared is going to give us this 7072, right? This number here is square root of that is this. So if you take this 7,072, don't need the decimals for now, 7,072 plus 31.97 squared. I'll say that again. Let's put it on the same screen. I just can't. 7,072 plus 31.97 squared. Add those two together. Take the square root of that, and you should get 89.971. And so that should help you find those things a lot easier. Oops. So let me get out of that. So here's what we're going to do on this. I'm kind of in charge, I think I've told you this before, of kind of moving things around to make it better. I know in this one, I think it's probably a little bit confusing. It seems like we've been in Chapter 7 for a while, which we have. But then there's this reading from Chapter 8, which is like 8.5, which hopefully everybody did. But it's kind of random that it's just thrown in there from 8.5. I actually usually cover that in Unit 11. That's the lack of fit test. But if you look on, and I was going to get to it today, we just kind of ran out of time. But let me take you out there one more time. If you look on SAS, if you look on Canvas, I've got the PowerPoints for that out there. And I'll show you that real quick. So if you look out here on Canvas, it's sitting right here. Unit 10, lack of fit test. Can everybody see my screen? I just moved over to the Mac side. Can you see a Canvas screen here?
No, Professor.
Ah, crap. Really? Okay. Hang on, man. I'm glad I asked. So if you go to Canvas, you can really just see if you go to Canvas. If you go to Canvas, it's a file in Unit 10 called something something lack of fit.
It's a PPT?
Yeah, it's a PowerPoint, yeah.
Okay.
My screen's taking forever, but if you, well, let me just get there. Come on, man. So if you go to Canvas, you can look at that. I can cover that on Sunday. Actually, I'll cover it next week as well. I'll just make sure that I open up that. Oops. No. So slow. Come on, your computer. Files, Unit 10, just so you can see it. live session. There it is. So Unit 10 lack of fit test. You can go ahead and check that out. It's just, actually, so it'll fit better into into the next unit, Unit 11. So you can check that out, and I'll start with that next time. And to today that I didn't quite get through was Hari had asked me a question about the regression fallacy, and we had talked a little bit about it on Sunday. So I prepared a little something for that, but we've kind of run out of time. I will cover that on Sunday if you want to go through that on Sunday. It's actually really quick. And so if you want to look at the video, if you can't make it to office hours, I'll cover that on Sunday. But it's pretty straightforward. So we can cover the regression fallacy then. But other than that, that's everything I wanted to get through, minus those two topics. How's everybody feeling? Awesome? Or yeah? No. Maybe. Okay. It's a lot. And I'm going to warn you, the homework is a lot. So maybe this is a good time to find a study buddy, or, I don't mind if you divide the labor up a little bit. Just what is not okay, do not, for your own education, do not say, hey, you do number one and I'll do number two, and then leave it at that. Okay, give me number one and I'll give you number two. If you're going to do something like dividing the labor, say, okay, I'm number one, you do number two, then I will look over your number one, or I'll look over your number two, and you look over my number one, and make sure you really look over it, because you're probably going to find an error, at least one, in each other's stuff. And in doing that, you'll say, hey, I did this way, and I did this other one the other way. So let me just kind of throw it out there. There's no real way for me to check it. I just really want you guys to own this at the end. But there's a lot. It's SAS and R. The rest shouldn't be nearly this involved. But you'll learn a lot from this chapter. I guess that's it, though. No questions? Everybody all right, all right? Cool.
Next Thursday, are we going to have a class? It's an inverter, right?
Oh, that is a good call. Yeah, what I wanted to do next Thursday, which I hadn't thought about in a while, is have a class, but in person. And then for those who can't make the immersion, we'll, of course, broadcast it. It's never been done before. I don't know if it'll work or not. And maybe we won't do it. I don't know. Maybe I'll take a poll. But we definitely, we took spring break, so we can't just take the immersion off. Oh, I see what you're saying, though. It'd be all new material. But it is the immersion. I did not think of that. I think what we'll end up doing is just trying to have a class in person. I'll make it fun. And we'll give, of course, a little extra time on the for the homework. So let's try that out. Nobody hate me for it. I think it'll end up being a positive. So yeah. So if you're not coming to the immersion, just log on at the regular time. If you are coming to the immersion, what time does everybody fly in? Are you coming in on Thursday? That might be one issue.
No, Thursday.
You come in on Thursday?
Yeah, we'll be there, but by the afternoon, and then there's like a reception. But they told us to go to class. That class was more important. So Thursday night.
Okay. Well, let's do this. Who again? I'm sorry. Just a show of hands. Who's coming to the immersion? Okay, so everyone. Oh, some. Okay, thank you. So it's not. Oh, Max, you're coming. Okay, but Alexandra, Ghislaine, and Robert, you're not. You guys are not.
No, I'm coming.
Oh, Robert is. Okay. So if you're not coming to the immersion, would you please just send me an email, and I'm going to send you a thing asking if you can if you're okay with watching the video for that one or logging in on a Friday. So I'd like for you guys to go to the reception, and when you're in town, I'll make sure to schedule with people at the immersion a time for us to kind of go off and have our own little class. Everybody that's here will be in town. I'll reserve us a classroom. We'll have that. I'll record it. I'll broadcast it live, but I understand that you haven't reserved those times on Friday. So if you want to just watch the video, that's fine. And if you want to meet in person, Alexandra or Ghislaine or whoever else can't make it, we can make that time to answer questions. But that's the way I'll plan it for now. I'm sorry I hadn't totally figured that one out. I forgot that that was going to overlap. But again, final, if you're in the immersion, we'll do it on Friday. Don't worry, I'll take care of the time. And if you're not, check out the video or we'll work together to make something else happen. But Unit 11, definitely study up for Unit 11. All right. Very good. Sweet. Are we ready to break out? We got another class coming up, and everybody's got things to do, I'm sure. Awesome. Great work tonight. Ghislaine, do you want to break us out? Yeah.
1, 2, 3, go.
Oh, you guys got to bring a good whammo next week.
Thank you.
I'll see you guys. Warm it up. Warm it up.